we need to do lots of things, and as I some attention. Hello there. Don't look there. All right. As I mentioned, the material we cover these days is going to be in the exam. As a matter of fact, 25 points are going to be in the exam. Okay? In some sense, that's bonus material, because if I cover it now and you pay attention, you will be happy. If you come here and you sleep, you're not going to be very happy. And you're going to say, the professor gave us an exam, but we never did any practice problems. Yeah, you never did any. Okay, so we need to, I don't know what's going on. What is this slide about? So we need to, this is something, okay. This is what I want to be, all right? So we need to summarize the criteria for stability of linear systems of ODEs. And then I want for sure to do one nonlinear example today, because there is a nonlinear example in the exam, okay? I usually tell these bonus things to undergraduates, so my apologies if I tell you that I give you that information as well, okay? All right, so we are looking at a system of equations that looks like this, okay? And we talked about different situations. We said how to identify first the critical points, right? And in most examples, the critical point was the 0, 0 point, okay? And I'm going to come back to it later today. But certainly, we recognize that the type of stability or instability we have, it depends on the eigenvalues of these metrics. So we would like sort of to summarize, and then at the end of the day, plot the results so that you can use them directly in your applications. So I remind you, this is only for the 2x2 system of equations. If you look for the eigenvalues, you have to solve the characteristic equation. So pay close attention to the way this equation looks. All right, so this is minus A1 and A22 plus the determinant of A, okay? And can you give me a formula for the sum of the two eigenvalues? So lambda 1 and lambda 2 is equal to what? Say it again. The trace, all right. And the trace is how much? A1 plus A22. And how about lambda 1 times lambda 2? Can you give me a nice formula for lambda 1 times lambda 2? You can actually think of a matrix, right, that has been diagonalized. And so lambda 1, lambda 2 in the diagonal, what's the determinant of that matrix? Lambda 1 times lambda 2 is equal to the determinant. Okay, all right. So effectively, I am going to call the sum of the two eigenvalues P. And so if I'm going to rewrite the characteristic equation as lambda squared minus P lambda plus Q equal to 0. So Q is going to be the product of the two eigenvalues. And obviously, you can look at the coefficients and compute directly in terms of the coefficients what P and Q is. And then I'm also going to define P squared minus 4Q. I'm going to call it a Greek delta. Effectively, if delta is positive or negative, we'll define if the eigenvalues are real or imaginary, or pure imaginary. So we need to have the delta there as well. And here is the explicit equation for these eigenvalues, all right? So by solving this second order equation. Okay, so what I'm going to do is I'm going to do a few cases, and then I'm going to show you the plot that is the most substantial part of all the lectures we have given on this topic the last few days. So I'm going to take a particular case of delta less than 0 and P non-equal to 0. Right, so let's see what this information means. So don't read the slides. If delta is negative, what does that mean for the type of eigenvalues we have? You remember delta was P squared minus 4Q. So if delta is negative, what does that mean for the eigenvalues? They are complex eigenvalues, so they are of the form A plus AIB A minus IB because they come in as conjugate format. And also if you take the product, lambda 1, lambda 2, so Q is A squared plus B squared, so it's greater than 0. Okay, so Q is, so this immediately implies that Q is greater than 0. Now, if you sum these two eigenvalues, lambda 1, lambda 2, the imaginary parts cancel out, so you get 2A. So if A is less than 0, all right? So we said we're going to get complex eigenvalues. So what is A? A is the real part of this eigenvalue. So A less than 0 means that the critical point is what type of critical point? So the lambdas are complex, and the real part is negative. So what type of, is it stable or unstable? It's stable, and because it's complex, it's oscillatory, right? So it goes towards 0 in an oscillatory manner. And how did we call this point? That's a spiral point, okay? So this is, it is not just stable, it's asymptotically stable, right? So, you know, as time goes, it will approach the 0, 0 critical point. And in the notes, sometimes I notice I try to eliminate this, but I forgot here. So when it says stable and attractive, is the same as asymptotically stable. All right, asymptotically stable means as t goes to infinity, it will go to the origin. But another way to say this is stable and attractive, you know. So if you take any trajectory, it will be attractive to the critical point 0, 0. And of course, if the real part is positive, then you will have, of course, a spiral, but it will, the particles will move to infinity, if I can say so. All right, so that's the case in the spiral point, the last one. So let me look at another case. If P equal to 0 and Q greater than 0. So if P is equal to 0, P, remember, is the sum of the eigenvalues. So lambda 2 will be equal to minus lambda 1. So Q is going to be minus lambda 1 squared. But there it says Q is greater than 0. And you look at this and you say the only way for lambda 1, lambda 2, which is minus lambda 1 squared, to be greater than 0 is for lambda 1 to be what? If I give you minus lambda squared and I tell you that is greater than 0, the only way to get that is when? When lambda is pure imaginary number, right? That's what you have, I hopefully you said. So what do we get when the real part is 0 and we only have an imaginary part? We get, you remember the centers, the circles, all right? So we get a stable center, but the center is not asymptotically stable, right? It keeps going around and around, but it never really will drop to the critical point 0, 0. Okay? All right. So immediately looking at the values of P and Q, right? In the second case, we already have identified this, okay? Now, I know when I show you this graphically, you will forget everything about this table, but I try to go through as many cases as I can. So let's take another situation now. So we consider delta negative. So let's take that delta is greater or equal to 0. So basically, the eigenvalues here are real, right? So we have this out of the way. So if we take Q to be positive, Q is the product of the eigenvalues. So if they are real and it's positive, means either both are positive or both are negative, right? So if they're both positive, what happens? What type of situation do we have? It's certainly unstable, right? And it is what we call a node, okay? And if they are both negative, then we have a node that is asymptotically stable, okay? All right. It's very possible. Okay, here's another case, all right? So here I only have the situation. The reason I only put Q less than 0 and nothing else next to it means maybe that Q less than 0 is sufficient to actually tell me the whole story. So if Q is less than 0, all right? When is that can happen? I mean, if you think about it, right? Only if the eigenvalues are real, and one is positive and one is negative. And that's when you get a saddle point. And a saddle point is by its nature, what type of, is it stable or unstable? What is it? Unstable, right? If one eigenvalue is positive, you know, it's unstable. All right, so basically the bottom line here is you don't really have to calculate the eigenvalues on these problems, right? What you need to calculate is P and Q, and then effectively look at the plot that I'm going to show you and immediately say this is what I'm going to get, and that's the end of the story. So let me, you know, rather than give you a mathematical definition, let me put this plot to literally define what I call stability here, right? And in particular, asymptotic stability. So let's call P0 the origin. So that's our critical point to start with, right? So we're going to take a trajectory within some sphere around the critical point that has a radius delta, okay? So generally, we're going to say that this trajectory, this point is stable if any trajectory that starts within the sphere of radius delta is going to find itself at a later time within another sphere of radius epsilon that's a function of delta. So basically, if you start somewhere in the neighborhood of P0, sometime later, you're going to be in the neighborhood of P0 as well, right? This is what we call stability in general. Now, how about asymptotic stability? Well, asymptotic stability will be sort of the same situation, but a little bit better, because if you start within the sphere of radius delta, any trajectory will eventually come back to P0. This is what we call asymptotic stability. So what, you know, in 2 slides before, these pictures have been put down in mathematical language, but effectively the schematic is all the mathematics that we need to know. All right, so here this is the critical point. We start, you know, a trajectory, let's say this trajectory outside within this sphere of radius delta, and eventually, as t goes to infinity, you are returning back to P0. All right. So this is the schematic that, and I have 2 versions of this actually. The next one is even better. So this is what we discussed up to now. The horizontal axis is the sum of the eigenvalues P. The product of the eigenvalues is the vertical axis. Delta equal to 0 is the equation. It's a parabola that defines P squared equal 4Q. You remember? P squared minus 4Q. Yes? All right. So delta negative is here. So that's when we get the complex eigenvalues and we have the spiral points. Delta greater than 0 is when we get real eigenvalues. So look at all the situations. Do you remember? So is this darker area stable or unstable based on the observations that we did before? Since you already read all the notes, all of this area, is it stable or unstable? Unstable. Can you pick up for me, just to make me happy, any of these dark areas and repeat for me why, let's say here, this is unstable, this triangular there. So look at all the quantities that I have and tell me why that spiral point is unstable. The only way a spiral point will be unstable is when? When the real part is what? Positive. Is the real part here positive? What makes it to be positive? Remember, the eigenvalues are minus p plus minus that square root of delta, and delta is negative. All right, so we're going to get complex eigenvalues, but it's minus p plus minus the square root of something that is less than p. So both eigenvalues, minus p plus minus square root of delta. So look and tell me, why is it one of the eigenvalues here going to come to have a positive real part? So I have P, the sum of the eigenvalues, is positive. The product of the eigenvalues is always positive because if they are imaginary, it's A squared plus B squared. Now, the sum of the two eigenvalues, lambda 1 and lambda 2, is equal to what? 2 times the real part. Right? The eigenvalues come in complex conjugate form. So lambda 1 and lambda 2, which is P, is 2 times A. And this region P is positive. Right? So basically, this is an unstable spiral point because the real part is positive. So here is a spiral point. Here is a node. Here is a saddle point for Q negative. And then we had this special case for situations for P equal to 0. What did we get for P equal to 0? What was the verdict before when P is equal to 0? Say it again? Pure imaginary, all right? So that's where we get this stable circles, right? But they are not asymptotically stable. So I think there is another plot. Hopefully, it's on these slides. Come on. Either my computer is misbehaving or my pointer is going to jump by 10 times here. Let me see. All right. So here is, no here, here it is, okay? Here is a nice plot that has everything with schematics on it, okay? So you can see the stable center. This is an unstable spiral, an asymptotically stable spiral. This is a stable node, all right? You can see all the trajectories basically converge to the critical point, unstable node, and a saddle point here. And you remember the definitions. You look at the saddle points, you see one direction that diverges, right? Goes to infinity, and then another trajectory, the other line that you see, it approaches to 0. So that's a saddle point. Somehow my nice pointer doesn't like me anymore, and I enjoy using this pointer. All right, so if you look in terms of the eigenvalues, right, everything you see is on this table, but literally in a homework or an exam problem, you are fine if you just look at this picture, you calculate P and Q, and immediately not only say what type of situation you have, but you are able to plot by hand this type of little plots. By the way, certainly in the exam, if I ask you to do a plot in the phase space of trajectories, use your imagination and plot it by hand. I don't want a computer. All right, just, you know, I mean, if, you know, here is a circle, there is a saddle point, these directions, and, you know, you can use your imagination and plot it by hand. Nothing fancy. Okay? All right. All right, so now I want to do a much more significant topic, and unfortunately we don't have a lot of time left in the course, which is who cares about linear system of equations, right? Everything is so nice and clear. How about nonlinear systems? Everything in life is nonlinear, so how about nonlinear systems? And nonlinear systems, of course, will be of the form. We're looking again for first order of ODEs, y prime equal f of y. And this function f will be nonlinear functions. So they are not going to be, you know, a11, y1, and a12, y2, etc. There will be some nonlinear functions of y. Let me just tell you what the big picture is, what the idea is. So let's say that 0, 0 is your critical point, all right? So what you're going to do is, to be able to say something about the stability of the nonlinear system, you're going to have to linearize the nonlinear system around the critical point. So effectively, what you will need to do, identify the critical point by setting f of y equal to 0. And let's say to start with, one of those critical points is the 0, 0, just for a discussion here. So if it is 0, 0, then you do a linearization of this, which means you actually write down a Taylor series expansion, and you only keep the linear terms. All right? And by the way, the constant term is going to be 0 if you do a Taylor series expansion around a critical point, isn't it? When you do a Taylor series expansion, is the constant term going to disappear? And why? Come on. So if I expand around a critical point, why is there is not going to be a constant term? Why there's not going to be a constant term? What's the definition of a critical point? Say it again. F is, at that point, is 0. So obviously, if I expand f of y around y0, f of y0 is equal to 0. Isn't it the definition of a critical point, right? Y prime equal to 0, yes? Okay? So effectively, when you do linearization here, the only thing that is going to be left is the derivatives. For example, if I linearize, let's say, y1 prime equal to the linear part of this, you're going to have something that is del f1 del y1 times y1 plus del f1 del y2 times y2, assuming that I do the expansion around 0, 0. If you do the expansion around some other point, I will tell you in a second on what you need to do. Actually, that 1 second is indeed 1 second, it's here. So pay attention. If one of the critical points is not 0, 0, but it is the point, let's say, AB, you can actually make the whole problem to look like your critical point is 0, 0. How do you do that? By changing variables. So instead of using y1 and y2, if your critical point is AB, work with new variables, y1 curly there and y2 curly, that they're y1 minus a and y2 minus b. Make sense? So like you shift your coordinate system so that your critical point becomes 0, 0. But you have to write a new set of equations for the new variables, all right? And the new variables are basically the old ones shifted by a and b. All right. I want to go directly to the so let me just say the theorem, okay, sort of without any proof. You know, we just take it here as a fact that when we linearize around a critical point, the f of y, the type of stability we get at the critical point for the nonlinear system, it's actually the same as the ones we get for the linear system. Okay, let me repeat it. If we linearize fy around the critical point, the type of stability we will get for our original nonlinear system will actually be the same as for the linearized system around the critical point. So this matrix A is the matrix of the first derivatives that I mentioned before, is the Jacobian matrix, and h of y are higher order terms, okay, that will not come in the linearization process. You neglect them. Okay? So if we can linearize the system of equations, and we understand how to discuss the stability conditions for a linear system, then we can use those conditions to discuss the stability of a nonlinear system around critical points. Now, even though it sounds like a trivial process, right, linearization, actually what you get wonderful things out of it that you will never get in a linear system, right? Because a linear system, the way we did up to now, had one critical point, 0, 0, but f of y equal to 0, it may have a lot of different critical points, and that will make the situation a little bit more complex. So let me go directly and do an example, right? We need to be sure that we at least finish one example today. So I'm going to take a pendulum that you have seen in your Dynamics 101 or Statics, I don't know what course. Please. Yep. Let me just go back. Tell me which slide. This one? Yep. Correct. You can describe it locally in a qualitative manner. I emphasize, in a qualitative manner. In other ways, when you linearize and you do all of these things, you're not going to get the solutions to the nonlinear system, but you will get the qualitative nature of the solutions. All right, so you will know what type of trajectories you have, but maybe you don't know exactly the form of the trajectories. You know what is stable, what is unstable. If you start here, what's going to happen, but the exact equations, they are not going to be there. Okay, so you get a qualitative answer, not a quantitative answer. So basically, you remember I emphasized that we get a sense of the solution that we can write in a napkin, right? You can say, oh, it's going to look like that. Because at the end of the day, if you understand what's going on and you can describe it in a piece of napkin, you know, then that's it. The rest is details that somebody else can do for you. Right? Some graduate student can work overnight and finish it up. Okay? So it's the qualitative nature of solutions. Okay, so let me go back to this pendulum thing. So what I'm going to do is I'm going to write the equation of motion. And you know, there are hundreds of versions of this problem. You know, I can put some damping and things like that, but we have nothing here but this mass moving and exchanging basically kinetic with potential energy. And as it moves, let's say we assume that the energy, the total energy of the system remains constant. So I am taking as a primary variable this angle theta, okay? So you can actually take the acceleration in this tangential direction, okay? And you can compute it because the velocity is L times the derivative of theta, okay? So you can actually write an equation. You can write Newton's law in the tangential direction. And I'm just going to give you the equation. Come on. The equation actually of motion is, I'm going to go directly to the, it's what you see here. Theta double prime plus k sine of theta equal to 0 for k is g over L. The mass has been canceled out. Okay? So this is the equation of motion. And this, obviously, it's a second order differential equation. And it's a little bit nonlinear because I have that sign there. Okay? So to be able to use the ideas from the linear system of equations, we're going to have to approximate. The first thing we're going to have to do is we're going to have to write this as a system of two equations, right, with two unknowns, right? So of two first-order equations. So how do you transform a second-order differential equation to a system of two first-order equations? Here I have second derivative of theta. So what will be the idea to take a second-order system and make it a first-order? So we're going to define one variable y1 to be theta and y2 to be theta prime. Remember this, at least until Friday. All right. But obviously, if we try to write this as a linear system, we are going to fail because there is a sine theta there. Can somebody tell me what are the critical points of this equation? I mean, obviously, there is an analytical solution. If sine of theta, if theta is a very small angle, sine of theta is about theta and then you can solve the solution analytically. But really, we're interested to keep the nonlinearity there, all right? So what are the critical points? One is, so what's the definition of a critical point here? So what critical points are we going to take here? remember before we had, a system as, we wrote it a system of first order ODEs, y prime equal f of y, and we set the critical points f of y equal to 0, all right? So what will be the condition here, basically, without having to do any algebra? Sine of theta equal to 0. And when is sine of theta equal to 0? 0 pi, 2 pi, 3 pi, 4 pi, etc. All right, so what we're going to, so we have a lot of critical points, okay? So what we need to do is, maybe we need to take, if we investigate what happens around 0, the critical point 0, then the answer, because of periodicity of the sine function, will be the same at 2 pi and 4 pi, etc. And then if we study what happens around the pi point, then the results will be the same thing for 3 pi and 5 pi, etc. All right, so let me study the stability for these critical points, right? And I'm going to work with the point 0, 0. All right, so we're going to introduce these variables, y1 equal to theta and y2 equal to theta prime, as we have written the other way around, right? So these are my two variables. And we're going to write the second order differential equation as two equations of first order. So will you agree with me that y1 prime is equal to y2? y1 prime is equal to y2? Yes? All right. And y2 prime is basically theta double prime, and from the differential equation it is equal to minus k sine of theta, and theta is equal to y1. So this is my two first order differential equations, all right, that, they're nonlinear because of that sign there. So based on the theorem we discussed before, to say something about the type of stability we have at the point 0, 0, we're going to have to linearize the right-hand side around the point 0, 0. How do you linearize y2? You don't, because it's already linear, right? You don't do anything. How do you linearize the sine of y1? What is the Taylor series expansion of the sine of x? Who is the guru in Taylor series expansions? What's the Taylor series expansion of sine of x? At least you should know the leading term. We even said it before, if x is small, sine of x is equal to x. Right, so what is the linear part of sine of x? X. So the linear part of minus k sine of y1, this is very important, around the point 0, 0. So when you write the Taylor series expansion, you say sine of x, x minus x cubed over, I don't remember, 3 factorial, etc., it's around 0, 0. Okay? So around 0, 0, the linearization of this will give you minus k y1. So let me put actually those equations together. All right, so do you agree that the linearized system of equations will look like that? Remember that y2 prime, we just said, will be minus k y1, right? That's the system of equations. Do you agree? All right, so I don't want to do any more calculations. So look at that matrix, the linearized matrix, the Jacobian basically, because this matrix involves the first derivatives of the right-hand side f. So look at this matrix and tell me what type of critical point the 0, 0 point is. How much is p in this picture? How much is p in this picture? How much? I heard it. What is p? P was the sum of the eigenvalues, right? Which is the sum of the trace. So it's how much? 0. Right? Can see? Yes? Yes, thank you. And how much is Q? I mean, this 2 by 2 matrix, right? If you write this, the two eigenvalues, right? If you try to compute, you have lambda squared plus k equal to 0. So the lambda is plus minus I square root of k, right? So what is q here? K. All right. So you told me P is equal to 0. All right. So I'm thinking of the big picture. P is 0, and Q is K, and K is positive because it's the ratio of two positive numbers, right? We define K to be G over L. Okay. So K is positive. So tell me from that picture that we had with the stability conditions, P equal to 0. And Q positive, what do we get? What type of point the 0, 0 point is? Circles, all right? So we get basically circles, and this is, I put this to remind you, we're actually getting the critical point is the center. It's stable, but it's not asymptotically stable, okay? Now, you can actually repeat now these calculations for the other critical points that are at the distance 2 pi from 0, 0. And in principle, you will have to linearize around, let's say, the point 2 pi. But you will get the same answers because the system is periodic, okay? I mean, that sign doesn't change when you add 2 pi. So we're going to get centers around 0, around 2 pi, 4 pi, 6 pi, whatever. So now we have to discuss what happens with the points pi, 3 pi, minus 3 pi, okay? So let's see what happens. All right, so we have to discuss about these points. So what is the first thing you need to do before, when you change the critical point and from 0 you go to, let's say, a point pi? What do we need? What's the first thing we need to do? What's the first thing we need to do? Shift the critical point to where? To the origin. And how you shift it? By removing basically from y1. So y1 was theta, so we're going to actually define a new variable y1, which is theta minus p. And y2 prime, y2 is going to be y1 prime, so it's going to be theta prime minus pi prime. So y2 basically is not going to change, but y1 is going to be theta minus pi. Now this is my differential equation. Can somebody tell me how we're going to, here is where you're going to do a mistake, all right? We're going to have to linearize sine theta, but around where? Right, so this is theta double prime plus k sine theta, but really you would be better off if you actually write this equation directly in terms of the new variables, theta minus pi and theta minus pi prime, okay? So if you look at sine of theta is sine of p plus y1. And what is sine of p plus y1? What is the relation of sine of y1 with sine of p plus y1? Minus, right? So if we have a minus and we put this on the other side, our system, instead of having a minus there, is going to have a plus k. Did we have a minus here before? I trust there was a minus, right? So now we have a plus. Big difference. Now you're going to say to me, but professor, I forgot to put the minus sign. It's not a big deal. Well, it is a big deal. If you forgot the minus sign, you are laughing, but you know, this is usually what students come and tell me. Sorry, you know, I was not feeling, it was late at night, and I just, my hand just, you know, put a minus sign, but it didn't really mean it, okay? So a minus sign. All right, so what is P in this problem? 0. What is Q? So what is Q? Negative K. All right, so I'm thinking now. P equal to 0, and Q, all right? Q is, you said, is negative K. So where is that leading me? Saddle point. Let's see what is going on here. All right? So you can see if Q is negative, all right, you get a saddle point. And here is this wonderful picture now that I'm going to show you. Come on. This is what actually I would like you to plot by hand, depending on your problem in the exam. All right? This is the phase picture of the system of differential equations, a nonlinear system. And you notice we get these stable circles, all right? And then what do we get here? We get these saddle points, all right? You can see, if you want to put arrows, that will make a lot of sense. You can see this path here takes you away from the critical point pi. This path converges. That's a typical of a saddle point. And the arrows obviously agree. And now, obviously, I have used a little bit my imagination because I put some trajectories on the top that somehow escape this, these critical points completely. All right, so they look to be a little bit oscillatory, but they escape these critical points. And actually, you can, in principle, you can guess, right? Because the further you are, all right, if you try to plot it, it has to look like that. Now, when I say it has to look, that's not a proof of anything, right? So if you look for a proof of something, you're going to have to do one more extra calculation, and I'm going to tell you now what that extra calculation is. Okay? So let me tell you what that extra calculation is going to be. So if you have the pendulum system, is there any quantity that is conserved as the pendulum moves up and down? What is conserved? Total energy is conserved, all right? So let me do a calculation and pay attention, at least until Friday, okay? Don't take pictures. It's in the slides. No, I thought you were lifting to take pictures. All right. So this is the differential equation, right? Theta double prime plus k sine theta equal to 0. So I'm just only going to look for the critical point 0, 0 here. So this equation, I'm writing it as, with my new variables as y2 prime equal minus k sine y1. We agree, right? Yes? There's nothing fancy there, right? Theta double prime is y2 prime equal minus k sine y1. But now pay attention to what I am doing. I want to calculate the trajectories, right, in the phase plane, which means I want really to find the slope dy2 over dy1. The plots that I have here is really y2 as a function of y1, isn't it? I mean, that's my phase plane, y2 versus y1. So I am going to write the time derivative of y2 as dy2 over dy1 times y1 prime. Can I do that? All right. And what is y1 prime? By definition, it's y2. Right? And suddenly, my equation that you see on the left-hand side has become a very nice ordinary differential equation, which we call it in 20 lectures ago. How do we call that equation? It's very nice. You can solve it immediately. How do we call that equation? Separable equation, all right? So we can separate y2 on the left-hand side, put everything y1 on the right-hand side, and actually you can integrate, and you can immediately see that y2 squared over 2 minus k cosine y1 equal to a constant. Now, can you guess if I do the appropriate definitions, if I multiply this, for example, with m times L squared, if I multiply everything by m L squared and define appropriately C, Can you see actually what this equation tells you? What is you think y2 squared over 2 times some constant? Kinetic energy. And what's the other one is the potential energy. Actually, you know, if you take, as the pendulum oscillates, and if you take the bottom to have 0 potential energy, right? So at a given location, the distance will be L times 1 minus cosine of theta, all right? L 1 minus cosine of theta. So the minus cosine of theta gives you this term. The other term is constant, and it's incorporated in what I indicate here as C. So effectively, for this problem, you actually know the trajectories. And if you want to go the extra step, what actually you do is, if you draw these things by hand, you can populate these things with different values of the constant C to indicate what is the value of the total energy. And you can see the trajectories that escape basically from these circles are basically having energy that is greater than K, all right? The trajectories corresponding to the saddle points have energy equal to K. And you know, you can put other values as you wish. Now, what I describe here for this trivial little problem may not be as easy to apply to more complicated problem. However, the methodology, it's a very powerful methodology in dynamical systems, okay? And unfortunately, I will not have time to cover it. I mean, I downloaded some slides from the next lecture to tell you a little bit more if you want to read it, but we're not going to be able to cover the details in the course. But literally, for these systems, we can actually calculate what quantities are conserved, and from those quantities, we can say something more qualitatively, if you like, about the trajectories on the faceplate. All right. It's 11:19, so what I want to do is I'm going to tell you what to read before Friday, because it's related with this example here, and it is sort of another application that will reinforce your training doing this type of problem. So I downloaded some lecture slides for Friday, and there is 2 little sections. One of them have to do with the dynamics of competing species. All right, so you can have 2 fish in a jar, you know, eating food and competing, and you see who survives. A very simple system of of nonlinear coupled equations. And then there is another sort of little section that has to do with population dynamics, you know. Cats eating rats, you know, okay? So who survives at the end of the day? And you will see those 2 models have practically the same architecture as you see on this picture. The only difference is the results may look completely different, but the algebra, exactly the same. There's nothing new, okay? So I am going to do those things on Friday, but so you don't tell me, but how can you do this on Friday and give it to us on an exam on Friday? Well, you read it today, so it is not on Friday. And if you don't want to read it on Friday, I can do something else on Friday, since you already have read it, right? Okay. Now, I'm not quite sure if I should have office hours tomorrow, because my office was completely packed yesterday. Completely packed, right? Your testimony? It was completely packed, so unless somebody mails me, my door will be locked. Okay, so I'll see you on Friday.